So we started with this algebraic structure called group, okay, and the group is a group is a non-empty set for our course in with a binary operation, and the binary operation is associative, and of course the binary operation has to give us this, that if we combined two elements with through that operation, it should be in the set. Then we should have identity, we should have inverse, and then we saw that some groups were like this set of real numbers with respect to addition, then set of non-zero real numbers with respect to multiplication, and complex numbers with addition, non-zero complex numbers with multiplication. We had integers modulo n, all right, with say addition modulo n. Then we had non-commutative groups like Hamiltonian group. And then we had this, say we have a group G, okay, and there is a subset H in that group. Then if H satisfies the group properties, we called H a subgroup of G. But in case H is contained in a group G, all we need to verify that H is a subgroup is that if AB are in H, then so should be AB inverse. And then we saw a group of permutations, which was like 1 onto map. In this case, I'm taking a permutation on 6 symbols. So in here, what we mean is this, that this is a map that takes 1 to 2, 2 to 4, 3 to 1, 4 to 5, 5 to 6, 6 to 3. So all such maps on these 6 symbols will form a group with respect to composition of groups. And the latest result that we saw was that all the groups, they are isomorphic to a group of permutations. And then we saw an interesting group called cyclic group, which is generated by a single element. That is, what happens is, in case if A is finite, then what will happen? Say this is A square, A cube, A to the 4, and after a while A will come back to the original place, or A will collapse to the identity. Okay, at a stage in case this is a finite cyclic group. And for an infinite cyclic group, what happens is that in an infinite cyclic group will just keep on going in the powers of n, where n is an integer, or that of A inverse. Okay, so let's just continue with these structures, and these structures are very interesting, and now we are over the midpoint in this particular course, but I shall try to post more videos for you later. Okay, now let us go with the the list of topics in the book. So this is the next topic, direct product of groups. So let's take that up. And what it says is that say we have two groups, and here I've formally indicated that O1 is the operation in the group 1, O2 is the operation in group 2. So G1 cross G2, which is just ordered pairs of elements in G1 and G2, will form a group if we take the binary, or if we apply the binary operation component wise. So for example, say we take this group here, R, say, remember this, that R plus is a group. So here we just took their Cartesian product, okay? So that becomes a plane, and say I have A1, A2, and I have B1, B2. Then all that will happen is that we will just take their sum to be A1 plus B1, and then A2 plus B2, as simple as that. and that gives it a group structure. Okay, and you can even see that if you look at this, the complex group of complex numbers with addition, okay, then you will see that these two are even isomorphic. All right, so this is how we have Cartesian product of two groups, and we can easily see this because if you just map this to A plus BI, okay, you can see at both the places they add component wise. All right, so that isomorphism should be very routine for you to be able to prove. Now let's look at a different case, and the different case that I'm looking at is, okay, is this one. That is, remember this R star, or the non-zero real numbers, that also forms a group with respect, sorry, that forms a group with respect to multiplication, right? So here we are going to write R star cross R star, okay? And then, yeah, here we are, okay? And then we have this. All right, so there we go. Okay, so what I will do first is this, that let's remove 0 as we are supposed to for both the places. Okay, so what happens is this one is R star, R star, where R star is the set of non-zero real numbers, and we are looking at R star cross R star, and our operation is just routine, actually very routine operation, A1 B1 A2 B2, that equals A1 A2 B1 B2, right? And this is the C star, right? And here we have the complex multiplication, right? Now say we want to define an isomorphism between these two groups, okay? All right. So if we look at this one, of course, in both of them, typical elements can be written as, remember, just the length from the origin, right? R cosine theta, R sine theta, and then we can write S cosine theta, S sine theta for another element, and here we can take in both the instances, if we want, we can even keep R and S greater than 0. Okay, all right. Now, if we multiply these two, what will happen? RS will walk out as a common factor, and here I should have taken a different angle. I'm sorry. Let me just make it like this. Yeah, I took a different distance from there, but then I forgot, just took that, okay? So cosine theta, cosine phi, then RS, sine theta, sine phi, bad handwriting. So this goes for up to here. Now in this case, what happens? In this case, if you look at two such elements, okay, if you look at two such elements, let me just take a different color. So say I took just like that R cosine theta, R sine theta, and then S cosine phi, S sine phi, then if you multiply them, what happens? in this situation, or when we apply the complex multiplication instead of that coordinate wise multiplication, what the product would be? The product would be RS. Of course, RS can be pulled out, and here I did not pull it out. I just saw that. Okay, so anyways, so here it will be cosine of theta plus phi. Okay, and here it will be sine of theta plus phi. So you can see the two are acting very differently in here, right? I mean, this part here and then this part here, they're acting differently, and we might suspect that we may not get isomorphism, and you may all have like a different kind of instincts, whether they are isomorphisms or not. There is another thing that's looking awkward, even though that would not rule out isomorphism to our present level of thinking, or we may also call it just one, right? So here 1 1 is the identity, here 1, which we may write as 1 0, is the identity, right? Now, if we go towards thinking that let's try to see or look at a counter example or look at a statement, okay, or look at a condition that might be violated so that they are not isomorphic. Okay, so when we start looking at that list, you can see both of them are commutative or non-abelian, so that doesn't work, right? Okay, then neither of them is cyclic, so that doesn't work. And then going further in the list, we can see this here, and that might work. That is, look at this here. If you look at -1, -1 is square, and 2 is the lowest power, so that this is 1. So this has order 2. Now remember this, if two groups are isomorphic, then they have to have the same number of elements of any given order. Okay, so if I come here on this side, look at -1, -1. Okay, now the order of this is 2, but at the same time, even 1, -1, the order of this is 2 as well, right? Okay, so here we have already found more than one elements with order 2. So what does it mean? That these two groups, okay, this C star and R star cross R star, they cannot be isomorphic, right? So, that was just for a discussion's sake, that if we are just taking same kind of thing, they may not necessarily, okay, work out in the way we thought. So let's take just a few more examples. Now let's turn our attention to finite groups. So I mean, a finite group, a very easy one is just the group with one element, that is the identity. So if we do that, if we take the direct product of this with itself, we get only, I mean, a group with only one element, that is EE, right? Okay. Now let's take a group with, say, two elements. Okay. Now the only group with two elements that we know is Z2, right? Okay. And now say we took the direct product of Z2 with say Z2. Okay. What shall we get? And we have we are looking at uh, addition modulo 2, right? So this is going to be 0 0, and I'm not putting bars anymore, remember? 1 0 0, 1, right? And then we got 1, 1, right? So this is the direct product of these two, okay? And you may notice that this is not cyclic, right? Why? Because the order of this is 1. The order of this is what? If you add any other two elements, okay, then you will find that their order is what? Their order is 2, right? So this is what we called the client's 4 group, right? So this is not cyclic. So what happens? It has 4 elements and it is not cyclic. It's client's 4 group. And now if you just look at it in an organized manner, and I'm going to post some readings for you, just in case you're interested in the details of writing these in organized manner, okay, then you may see that there are only 2 groups. We may say up to isomorphism, okay, and later on, when not necessary, we would even drop this statement. Only 2 groups of order 4, okay, one of them is what? Z2 cross Z2, and the other one, I wish I was talking to you live, but I'm not, so, but the other one is for any positive integer. There is always a group. Who is that? Integers modulo that integer, right? So this and this, these are two different ones. They cannot be isomorphic. One reason is this is not cyclic, and this is cyclic, right? Now, let's go to, say, order 3, okay? Now, for order 3, what we have is, well, for order 3, this is the only one, right? Because 3 is a prime, so it's a cyclic group, right? Okay, and cyclic groups are abelian, all right? And this turns out to be the only group that we have of order 3. Now, let's see if we took Z2 cross Z3, right? So say I have Z2 cross Z3, then what the elements will be, we can write them quickly. I could have written them, but I think it would not hurt to write them quickly. And now here we have to be careful that in the first component, we are taking addition mod 2, and in the second component we are taking addition mod 3, right? So we got 1 1 1 2, right? And then 1 3, right? Okay, then we will have say 2, oh no, 2 is 0 in the first component, right? So 2 is 0, so I made a mistake, right? Okay, let me fix it, okay? All right, so this is 0, and I made another mistake here. I was adding modulo 3, so that should have been 0. So we have to have 1 0 0 1. Likewise, we have to have what? 2 0, right? And 0 2, right? So how many elements would we have here? We would have 6 elements, right? Okay, and we see here that we got 7 of them. So let's see what we got extra. Again, this we got extra. I'm not thinking, right? So I am so sorry here. Now we got 6, okay? So let me first officially say sorry. Okay, all right. Anyways, so this is Z2 cross Z3. So, and we didn't even write it in order, but I hope I wrote it correctly, right? Okay. Now let's see in Z2 cross Z3, do we have any element of order 2 or 3 or 6 or what the orders of all these elements are? Okay. So 0, 0, we already know the order, right? Yeah, its order is 1. And then here, when we go to 1, 1, notice this, the order here is 2 and the order here is 3, right? So we will expect the order of this element to be the lowest common multiple of 2 and 3, that is 6. So let's just verify, doesn't hurt. Okay, actually we got what? We got 0, 2, we are looking for 0, 0, right? Okay, so here we will add 1, 1. And when we do that, what do we get? Then we get 1, 0. Okay, let's bring in 1, 0. All right. Uh, so let's bring in 1, 0 here and then add 1, 1 to it again. 1, 1. So then what do we get? Then we get 0, 1 now, right? How many times have we added now? This was power 2, power 3, power 4. All right, now we are getting to power 5. Okay, so this, then 1, 1. All right, so we got what? 1, 2 here, right? Okay, so we have reached up to power 5. And then what happens is, let's add 1, 1 again. And then what happens? 1 plus 1 is 2, which is 0. 2 plus 1 is 3, which is 0. So this element has order 6, and this has 6 elements in here. So what do we find then? We simply find that this is this group or this direct product actually is generated by just this element. And who else is generated by an element of order 6? That's Z6, right? So here you can see that Z6 is isomorphic to, right? It is isomorphic to this product, right? And there is another group with order 6, if you remember, and that's who? That's the permutation group on 3 symbols, right? Or all those transformations of equilateral triangles as you saw. So here you will see, and I'm going to give you link of a detailed discussion, you know, in the post, okay, that for order 6 we will have these two. This is abelian and cyclic, which is Z6, and of course a cyclic group of any positive integer order always exists, and this is a permutation group, and this is, as you know, is not commutative, right? Okay, so these are, so we got these two groups of order 6. Now we are doing it at this level, but like about 16 years ago, all finite groups, all the groups of finite orders have been classified. We wouldn't have tools to discuss that in this short a time. All right, at the same time, I don't have, I mean, I'll confess, I haven't kept up with my reading even to be able to, you know, deliver a lecture in detail on that. But so anyways, so we talked about groups of order 1, 2, 3, 4, 6. And actually for order 5, 5 is a prime number. So for 5 also there is only, there is only one. And who is that? That is simply your Z5, right? Since 5 is a prime, that will be prime ordered, and same for Z8. Okay, all right. And not Z8, sorry. For 5, this is Z5. Uh, for order 8, you will have more. Remember, you first of all, you already have Hamiltonian group, right? You had dihedral group. So I'm going to post the list for you, because what I'm going to do is that I'm going to keep this video shorter, all right? And I shall just, you know, just post some well laid out notes for you, okay? In which you shall see that how do you use these to classify groups of given orders, okay? So, so we have gotten this, and for Z8, you will shall see in there. And these actually, this direct product has many applications in cryptography, because when you look at a binary string, that can be seen as a, uh, as an element of direct product of Z2 with itself, quite a few times, depending on how long a string are you looking at. All right. So, so not only cryptography or data security and error coding and all that. And I will do this and that. Cryptography and error correction codes, all those are in your book, which is Abstract Algebra and Applications, okay, or rather Theory and Applications by Thomas Judson, available free on the internet, okay. And there is a very nice lecture about application of this in particle physics that is by Sean Carroll of California Institute of Technology. I'm going to post a link of that for you also. Okay, so this was the direct product, or you call it external direct product. Okay, and what I would ask you to do is this, instead of me just, so this one is, I shall post Sean Carroll's video, okay, who is from California Institute of Technology. I don't know why I'm rewriting it, okay, of technology. Do this, that likewise there are internal direct products, okay. All right, and the book does a good job of explaining it, and I will leave that on, for you to just read it from the book. Okay, because our time is like, we have progressed much faster, all right, and we have limited time left for this particular course, okay. So, and it's time to like wrap up the things in next few videos, okay. So I will leave that reading on you. So once again, this part and some more discussions that we will do, okay, will be, one of the aims would be to classify or look at the classification of groups of certain orders, and of course there are many applications, all right. uh, I said error correcting codes, okay, messagings, all that thing, all those kinds of things which I have not worked with, okay. And so the applications in those areas. So let me stop this particular presentation here, and then I shall see you soon with more like, with a few more those 50-minute presentations, okay? All right, so see you then. Thank you.